Today, I'm really glad to join you to discuss science, collaboration, innovation across traditional boundaries. My name is Vicki Grassian. I'm a distinguished professor and currently the chair of the Department of Chemistry and Biochemistry here at UC San Diego. I'm talking to you now from the UC San Diego campus in the chair's office. From this office, I can see beautiful Ravel Plaza with all of our tented classrooms that we're now using. And I see students walking around, even though it is dark outside. And it's just great to be here on campus and great to be here with all of you. I really appreciate having an opportunity to be part of this Exploring Ethics webinar series put forward by the Center for Ethics in Science and Technology. So I want to start off by just taking a moment to think about some of the grand challenges of the 21st century. For example, we all know there are challenges associated with access to clean water and water resources. Some of the issues that have come up include the fact that there could be lead in people's water. There's drought, so the amount of water available is small, and there are concerns about that, especially here in California. We think about drought a lot here in California. There's agricultural runoff. That too can cause contamination in water, making water not drinkable for people. So that's one of our grand challenges. But we have many. We have grand challenges associated with clean air, even though the Clean Air Act was enacted many, many decades ago. But we still think about air quality outdoors as well as indoors. Has been discussions that I've been part of for quite a while now. What are the issues? There are pollutants from many sources, including gases such as ozone and nitrogen dioxide or other nitrogen oxides, as well as aerosols, which is something I'm going to focus on quite a bit during this talk this evening. So that's a grand challenge. What else? Climate change and the impact of a changing planet. What are some of the issues there? We still have increase in greenhouse gas emissions. We talk a lot about CO2 or carbon dioxide, but there's also nitrous oxide, methane, and other greenhouse gases whose emissions are increasing over time, not decreasing. And then there are the consequences of a warming planet. We're living it, we're seeing it right now. Whether it's more hurricanes that we're seeing, but just many consequences to a warming or a changing planet. The global pandemic, another grand challenge of the 21st century, COVID-19. For many of us, this is the first time we've been in a global pandemic, right? The last one was about 100 years ago. What are some of the issues that we're seeing now? Controlling disease transmission. New variants, another new variant has just come on board. Another thing to worry about. We were worried about the Delta variant. Now we have Omicron variant. Vaccinations. Then we think about things like ventilation, masking, all of these things related to the global pandemic that we're in, the COVID-19 global pandemic. And then, you know, the whole issue of environmental justice, where communities are not similarly impacted. So we have communities, poor communities, communities with people of color being more impacted by all of these issues: water quality, air pollution, health disparities, climate change, another grand challenge of the 21st century. So this is the things that we think about. This is what is going on. And so what do these grand challenges require? They require science, they require collaboration, and they require innovation. But that might not be all of what's required. So let's keep on thinking about these grand challenges and what they require. And when we think about these grand challenges and the science that needs to occur, collaboration, innovation, it needs to occur across traditional boundaries. That is, we need to have many people involved, the different backgrounds thinking about these problems. In fact, grand challenges require what's been called convergence research. So here I have some definitions. I like to give definitions so that we're all on the same page. And I take this definition from the National Science Foundation, which defines convergence research as a means of solving vexing research problems, in particular complex problems focused on societal needs. And that's what we've been talking about right now with our grand challenges: clean water, clean air, climate change, and how it impacts all of us. So this convergence research involves integrating knowledge, methods, expertise from different areas and forming novel frameworks to catalyze scientific discovery and innovation. So we can think about convergence research as it relates to other things that we've talked about: interdisciplinarity, multidisciplinarity. I think people are starting to use this term transdisciplinarity, where we really focus on the problem and we all bring our expertise together in order to solve these grand challenges, in order to make an impact in terms of having clean water, clean air. How do we deal with things like climate change? Now, here I am sitting at the University of California, San Diego campus, and I'm at an academic institution. But in general, our institutions are all organized around traditional boundaries. So I know the physics department is located in a building nearby. I know medicine is in another part of campus, engineering also in another part of campus, biology is nearby. I'm in Urey Hall, where a lot of chemists are. There's also biologists and physicists in this building as well, but pretty much we don't really see anyone in public health. They're in another part of campus. And I think I've walked by the social science building a few times on campus, but we are organized around traditional barriers. So I mentioned that in terms of, the academic institutions, but even our federal funding agencies, and I'll pick on the National Science Foundation for a moment because it's the one I know the most about. If you go and look in their website, you'll see the Mathematical Physical Sciences Division, which then has chemistry, physics, mathematics, all the traditional boundaries, all the traditional disciplines. So that's how our institutions are organized. And even within a traditional boundary like chemistry, we're even sub-organized into organic chemistry, inorganic chemistry, biochemistry, physical chemistry, analytical chemistry, and environmental chemistry. So our problems need this transdisciplinary approach. Our grand challenges are transdisciplinary in nature, yet all of our institutions are focused on traditional boundaries that have been around for a very long time. So I think some issues arise. We can even call them ethical issues arise. These institutions are grounded in traditional disciplines. Problems, grand challenges need convergent research and transdisciplinary approaches. So that's sort of what I wanted to set up as the situation at hand. And I want to go through some things during the course of this evening to have you think about these issues. Okay, so first I'll just tell you a little bit about some of the things that I'm interested in, and I'll focus on one aspect for you today. But I've been doing research for 30 years. My independent career has been going on for 30 years. I provided a lot of leadership in STEM through my research, through my teaching. My own interests are in tackling complex problems. That's what I've been interested in for many, many years. I like to be involved in teaching, mentoring, and advising students across different disciplines. So in my laboratory, we might have chemistry students, but we have engineering students, we have environmental science students, all working together on problems that we're interested in. I've been very involved engaging in diversity, equity, and inclusion efforts. So my lab is very diverse, just from these students in different disciplines, but also with very different backgrounds. They all bring a lot to the table in terms of our research and how we think about things. I've been involved in leading workshops and writing workshop reports for foundations and federal agencies. Right now, I'm working on something with the National Academy of Sciences, where you sort of define problems and discuss what are the needs, the research needs that are essential for moving forward. That's been something I've been involved in quite a bit, as well as leading what I call center-enabled research, and we'll get back to that centered enabled part in a little bit. My own research I described as being working on environmental interfaces, and I have that broken up into a few different things. I'm very interested in aerosols, which will be the topic of this discussion today. I've also worked on nanomaterials, their environmental and health impacts, and I have a research going on related to indoor surfaces and indoor air quality. I won't get a chance to talk to you about that today, but these are the things that I think about in my laboratory. What I want to focus on today, I want to focus on aerosols because they're amazingly interesting and they have so many different impacts that I want to share with you today. And then think about some of the issues that we're thinking about, the grand challenges and how aerosols are involved in some of those grand challenges. So again, definition, I like everybody to be on the same page. Aerosols are defined as solid or liquid particles suspended in a gas, typically air, okay? And they have dimensions between what's called micrometers to about 100 micrometers. So if you think about a hair, that's about 80 micrometers. So a micrometer is 1 × 10⁻⁻⁶ meters. Again, a hair is about 80 one piece of hair that you can see is about 80 micrometers in diameter. This is also termed particulate matter in air, so I just wanted you to know that as well. And what I would say is that the impacts of aerosols are quite extraordinary. And I'll take you through that now. So today I'm going to talk about aerosols and their impacts, and we're going to go back to that thinking about convergence research as well. And I'll take you through just all the different ways one can think about aerosols and spray cans, inhalers, in air quality, how it affects human health, how it even impacts climate, how it can be used to geoengineer the Earth system. I'll mention that. And then also more recently, how we think about disease transmission as it relates to viruses such as the coronavirus in aerosols, especially when they accumulate indoors. So this is where we're going to go. We'll talk about all these things. So here's aerosols. Maybe most of you are familiar with spray cans. You can produce aerosols. I've used them, you use them. We don't use them quite as much as we used to for various reasons. Here's a picture, this is my own picture of my own inhaler, which produces aerosols. And, you know, a lot of people have asthma, a lot of children have asthma, a lot of us are carrying our rescue inhalers with us. And we use that when we feel like we're having an asthma attack maybe coming on. And so we all know about aerosols from these different perspectives. But aerosols are also in air from everything from volcanic eruptions. That's what's shown over here in this slide. Also from smokestacks, we can see aerosols coming through. You can also have aerosols from dust storms that can happen anywhere in the world, but mostly in the more arid regions, but they can happen in Phoenix or Australia or China or just anywhere in the world. The Middle East, a lot of different arid regions, and you see these big dust clouds coming through. And also aerosols are produced from car exhaust, and just you can see that from this fuzzy picture with these cars all backed up, and that's from aerosols getting into the air. So it affects our visibility as well. This is how I like to look at aerosols. So so these pictures are sort of a zoomed out look at aerosols. I like to take a zoomed in look at aerosols, and you can see these particles. What I'm showing you here are solid particles of volcanic ash. Also showing you particles, what we call fly ash from either coal combustion can produce fly ash. We also have mineral dust particles that we're showing. We're zooming in using an electron microscope to see these things in this micrometer size range. And we also have these aerosols produced from cars. Aerosols are really amazingly interesting for a number of reasons. I already mentioned that they have this size range from like very small to larger, about 100 micrometers, to like very small, like 0.002 micrometers. They also differ very much in their chemical composition. So aerosols impact air quality. I've already given you the definition, but we do have regulations for outdoor air, PM 2.5 regulations that are regulated by the EPA. And that's related to particulate matter less than or equal to 2.5 micrometers. So that's what our regulations are all about. And I make a point here that I want you all to hear very, very well, is that this is the regulation that we have for particulate matter in outdoor air. Okay, and what I will tell you is that particulate matter in indoor air can be higher than that of outdoor air, and it's really not regulated. Okay, but if you're going to have health effects due to particulate matter, and that's why we have these regulations for outdoor air, there's no regulations for indoor air, but the levels can go very high, higher than what we regulate outdoors. There seems to be some missing link, if you will, of issues related to indoor air quality that we don't quite have as well known as we do for outdoor air. So the other thing important to note is that this particulate matter tends to be part of the air pollution that we all think about and worry about. And what I would say is that aerosols are not evenly distributed. So what's shown here is, this is a magazine that I read called Chemical and Engineering News. All of my degrees are in chemistry. You can even see my blanket behind me, which is a blanket of the periodic table that I got from a recent American Chemical Society meeting that was in San Diego a couple of years ago. So this is a magazine I read all the time, Chemical and Engineering News. And they had an article that I thought was very interesting and I wanted to share with all of you. So I had agreed to give this talk early in June, and then I was saving things so I can present to all of you. And what it shows is that there's a look, here's a look at air pollution inequalities within cities. So this is a heat map. So when you see red, that means there's a lot of things like particulate matter and ozone in that region of the city. In sort of the grayer areas, it's not as much. Yellow also has some, and so forth and so on. And so this is a heat map which clearly shows that in the same city, people are being exposed differently across the city, okay, and that there are pockets within the city, neighborhoods potentially near industrial areas, potentially near highways, whatever the source is, that have greater amounts of particulate matter and pollution in their air. So this is just something that, like I said, I read in Chemical Engineering News, and I wanted to share with all of you. And but then also then in October, here in San Diego, we see that we have the same thing going on. And there was this editorial. I read the Union Tribune every single morning. I want to see what's going on in San Diego. And I also like to do some of the puzzles that they have in the newspaper. But this is what I wanted to look at here. It's clearing the air. And this is what some of the opinion piece says. In our San Diego neighborhood, pollution's literally everywhere. And then another, all too often, no one listens to us or cares. And then finally, the last is the Port of San Diego has a new commitment to clean air. So clearly here in San Diego, just like in that article I was showing you from Chemical and Engineering News, we have disparities in our neighborhoods in terms of pollution. And we know that. We already know that. And here it is written out in the newspaper. And this is something we need to think about. This is something we need to talk about. This is something we need to fix. And so I just wanted to point out that these inequities in our air quality is happening in every city. It's happening in many places. And it's something that we need to be very aware of. And it's something we need to fix. So another topic that I like to think about, being here in San Diego, and we have the beautiful beaches here in San Diego. We have oceans right here. We get to walk along the ocean, and oceans are a source of atmospheric aerosols. Some of these are made of just salt, like sodium chloride, that gets into the air. Again, here is one of my electron microscope images showing different types of particles that get into the air from wave breaking and bubble bursting at the ocean air interface. So oceans are a source of atmospheric aerosols. And one of the things that I think about is what happens when water becomes contaminated. So if you look at this picture over here on the left, pretty much what will happen is a warning sign will go up. It will tell people not to swim in the water because it's contaminated. If some contamination, some sewage gets into the water, we know that happens quite a bit here, actually. We often hear about Imperial Beach being contaminated, just for one example, and signs immediately go up, do not go in the water. It's a health, it's health issues associated with this. Exposure may cause some illness. But on the other hand, I want to put another sign up. And the other sign that I want to put up is contaminated air, because I just told you that these aerosols that come from the ocean due to wave breaking and bubble bursting, also happening when the water is contaminated and it's getting into the air. And that exposure can also cause illness. We don't talk about that so much because it's really easy to put up a sign that says don't go in the water, and it's really easy to make sure people don't go in the water. You can monitor that. You can say, get people to get out of the water if you see anybody in. But what about breathing the air? Okay, that's just something that's not really able to control, and so we don't see these signs. So when water becomes contaminated, whatever's in the water can also get into the air. Okay, so that brings us up to what I wanted to talk about next, was health effects of atmospheric aerosols. So there we were talking about contamination getting into the air, but just in general, it's pretty well known that aerosols and particulate matter, high levels, especially due to pollution, causes health effects. It's been known for many years, at least 1993, if not more. But I just picked this particular article now, which is 30 years ago or so. And what we see here is that there's an association between air pollution and mortality in 6 US cities. And so this is just the tip of the iceberg. There are many, many studies that have looked at air pollution and mortality, plus other health indicators, emergency room visits, and a lot of them are related to these aerosols, particulate matter getting in the air. So we've known that it's had a health impacts for many years. And we're learning even more and more and more. And I want to sort of tell you some of the latest science. So we know for many years that particulate matter, because we can breathe it in, these aerosols, especially the particles that we're regulating, that is PM 2.5, that is 2.5 micrometers, or 2.5 times 10 minus 6 meters, 2.5 micrometers, that can get into our lungs. We can breathe these aerosols into our lungs. And so for a long time, we know that it can impact people, especially people with COPD, chronic obstructive pulmonary disease, people with asthma. We know that there are health effects associated with the lung with particulate matter. We also know that can impact particulate matter can impact heart health, cardiovascular system. It's been shown that people can even have heart attacks after being exposed to high levels of particulate matter. Now, most of these studies are they're not individual people, but they're studies done, epidemiologists study these things, looking at large populations and correlating that to days in which there were high particulate matter in the air, high pollution days. So we know that it affects heart to cardiovascular system. But what's really new and really what I would say, the least is known, and what's new, and I think really deserves a lot more attention, is that aerosols and particulate matter and pollution can impact brain health. And I've read a couple of papers on there, and it's not because I don't want to read more papers. I will just tell you there aren't many more papers. But one paper that came out a couple of years ago looked at particular air pollutants and basically their ability to cause dementia in older women. And again, this is a study looking at epidemiology studies, looking at many people, not just a few people, just looking at what was going on and controlling for other variables and suggesting that that it was causing dementia in older women, high levels of particulate matter, that people were more prone to dementia. Science magazine did a story on it. They called it The Polluted Brain. And pretty much they speculate what is going on. What's the mode of attack? Why would particulate matter impact the brain? One thought is that these particles, especially small ones, the smallest one can pass through the blood-brain barrier, maybe getting into the brain. That could be one mode of attack. Another mode of attack was the fact that we were breathing these particles in, and then cytokines were being formed that then can get to the brain. So really not much is known, and this is something I think is really something that needs a lot more attention. So those are some of the health effects associated with particulate matter and aerosols. Aerosols also impact the Earth's climate. So I told you we're going to talk a lot about what aerosols can do. Aerosols can also impact the Earth's climate. And so how can they do that? Aerosols can impact the Earth's climate by interacting with solar radiation, the sun, radiation from the sun, and also that aerosols can nucleate clouds. So if you look at this picture of the sun, we have the sun and light rays coming down on the Earth's surface from the sun, and these little aerosols can actually scatter some of that light back into space. Other light can impinge on the Earth's surface. And so because it can scatter light back into space, it can actually remove some of that sunlight away from the Earth. In fact, it's thought that some of the aerosols that we have in the Earth's atmosphere is actually offsetting what is going on with CO2 by actually causing this cooling. So when it scatters away from the Earth's surface, it actually is a cooling effect that the aerosols are imparting. Aerosols also can nucleate clouds. So oftentimes in the atmosphere, there's high levels of water vapor that have yet to condense into a cloud. And these aerosols, these particles, can actually provide a seed for water to condense on and thereby helping cloud formation. Once you have the cloud formation, then again, some of that solar radiation reflects back into space. And so that again causes a cooling effect, offsetting some of the global warming effects of greenhouse gases. So that's really interesting that aerosols can affect health, can affect climate. And now people are starting to say, well, can we use aerosols? Can we use them in a way, even put more aerosols out there, maybe even in the stratosphere? We're here in the troposphere. The stratosphere is another level up, if you will, to cool a warming planet. Can we use them? Can aerosols be injected into the upper atmosphere to scatter sunlight and therefore cause a cooling effect of the Earth? So sort of balancing out, if you will, increasing CO2 and other greenhouse gases. So that's the thought that people have. A lot of scientists can just do back of the envelope calculation, figure out what might happen with the light if it hits these aerosols and reflect back into space. Can I calculate a temperature change? How can this be used to geoengineer the Earth system? So that's a thought out there. And a couple of years ago now, there was an article in my favorite magazine, Chemical and Engineering News. And here I describe it better, weekly magazine of the American Chemical Society. Will the world be ready for solar geoengineering? That was the question put forth. And the reason why that was in Chemical Engineering News was that there was a Harvard scientist, or actually a chemist, who was interested in starting a small-scale solar geoengineering project. You can look it up on the web if you want to learn more about it. And the idea was to release a plume of aerosols into the upper atmosphere, so not where we're breathing, but the upper atmosphere, to just study what would happen, their physical chemical properties. Would they change in the upper atmosphere? Would they do what we thought they were doing? Would something unexpected consequences happen? So that was sort of the question. And so, those things always kind of worry me because I don't know if we can think about all the feedbacks. And the chemist who was actually leading this effort was Frank Koish, and he said, I actually think it's a terrifying concept. So he was leading the effort. That's what he said about his experiment of putting aerosols into space, into the upper atmosphere, I should say. And then he added on to that, but at the same time, if you look at predictions of climate change, I think they are also very frightening. So he's trying to balance, this is an ethics webinar, these ethical issues, this doesn't seem good, that doesn't seem good, what should I do? I want to help. I want to do something that can help. But what was really interesting is he had planned the experiment in a fairly remote region in Sweden. And it turns out that the experiment didn't happen because indigenous people called for Harvard to shut down the geoengineering project. They didn't like it where they were having it, where they were going to do the experiment. It might be remote, but there were still people living there, and they didn't want it to happen there. And I think that it did get shut down, and it was going full steam ahead, but it did get shut down. So here's a case where people questioned what was going on in their background, and at least in this particular case, that experiment, I believe, is still on hold. So I just wanted to tell you about that. I want to also talk about, as I sort of keep on going and approach toward the ends of what I want to say about aerosols. What about the aerosols in the air we breathe indoors? Kind of mentioned indoors already, but I will tell you that it's been known for a long time in some developing countries that smoke from cooking stoves it has a huge impact on health and is actually a major environmental cause of death. So here are people just cooking in their homes without ventilation. like we have, and they're exposed to high levels of aerosols, as well as carbon monoxide and other even nitrogen oxides. And so here's an example of that. And we've known that for some time. But even in our own homes here in San Diego, if you need to use your vents when you're cooking, sometimes if there's bad outdoor aerosols that can come indoors, plus other things that people do in their homes that introduce aerosols, but not quite as bad as this. But what we've all been talking about a lot lately is that people produce aerosols, okay? And so when you're singing or talking, right now I'm producing aerosols, you produce aerosols. And this is a diagram I took from my colleague, Kim Prather. So the picture on the left is just showing someone producing aerosols as they're speaking. So the aerosols are sort of the smaller particles, the droplets, they tend to come out of the air more quickly, they're larger. They are important because now we know that these aerosols can contain virus, contain the coronavirus. And in fact, it's thought that aerosol transmission of COVID-19 is one of the most important mechanisms for transmitting the disease. So now we think about aerosols and how they transmit disease, and they can even the virus, but also maybe even the flu people are talking about. And you know, in this paper by Prather et al. By Kimberly Prather, my colleague, she shows, you know, why masks work, how masks work, to make sure that we are we can mitigate being exposed to virus-laden aerosols. And so that's been something that now has been in discussion quite a bit. So these are some things that have come forward, especially as it relates to COVID-19. And so if we think about the science, collaboration, and innovation, especially as it relates to COVID-19 disease transmission, what has been shown is the latest science shows virus and aerosols. Scientists, we'll call them aerosol scientists, some are chemists, some are something else, engineers, physicists, typically outside the medical community, but they want to collaborate and innovate to change the existing paradigm for disease control. But then you have people who work on hospital implementation specialists, I'll call them, and they have to follow certain protocols. Maybe a certain body has to agree to what they will be doing under different conditions. There's a lot of protocols in hospitals that have to be followed. And you can't just say, I read a great paper that showed this in, you know, Science or in some other journal, and I'm going to change how we do things. So sometimes their hands are tied, or they don't see a need for a paradigm shift. They're not convinced. It's only been 2 papers. You haven't shown this enough. You haven't shown that enough. So clearly we're starting to see where even science, collaboration, and innovation may not be enough. And so when we think about these aerosols, I've just given you so much information, how they impact atmospheric chemistry and air quality, climate, health effects, disease transmission. Many disciplines are needed to understand any of these areas. And so, you know, where do we go from here? You know, so, you know, we need this transdisciplinary science, this convergence research, which involves collaboration and innovation. And now I'm going to add another stool here, if you will, another leg of the stool, I should say, and that is implementation. And so that's something that's just being discussed right now, and how we do this. So where do we go from now? How do we do transdisciplinary science, which involves collaboration and innovation, as well as this implementation? So let me just say, I talked about the university, the academic institutions, other institutions being grounded in disciplines, but there's a role of research centers and institutes to bring people together. And I have listed a few of them. For example, the Center for Aerosol Impacts on Chemistry of the Environment, I'm the co-director of CASE. That's something we have here at UC San Diego. I work with Kimberly Prather, who's the director of CASE. That's one where we can bring people together to tackle important issues, to engage scientists and engineers, to innovate and collaborate. I've been involved in other SEGRA when I was a faculty member at the University of Iowa before I came to San Diego, focused on global and regional environmental research. I was also part of the Environmental Health Sciences Research Center and also the Nanoscience and Nanotechnology Institute at the University of Iowa, which I actually led for about a decade. And that's what we do. We bring people together through these research centers and institutes. And where do we go from here? But I just mentioned there's this other piece that's really important to everything, and that is implementation. And so this editorial just came out in November 2021. So I'm collecting all this information for everybody so I can give you the latest of how people are thinking. It's called A New Lane. It's an editorial, A New Lane for Science in Science Magazine. And so it states, COVID-19 has shown the world that knowing what to do does not ensure doing what we know. How do we take what we know and implement? So in this article, they go on to suggest that science needs to add another lane, one called implementation research, thinking about things like implementation scientist. How do we take knowledge and turn it into something that we can use, people can hear more about, know more about? How do we do that? We need to be doing that. I think COVID-19 has in fact shown us something we really, really are missing. So where do we go from here? I'm throwing out to all of you, implementation science, an important, or implementation research, an important component to solving societal problems. And what I would say is, why can't we do better? Or maybe I should say we need to do better. We should do better. I think that's what we've learned during this global pandemic. Our institutions are disciplinary in nature, how we cut it up. Our societal problems are transdisciplinary. Our research centers / institutes the answer. That's how I've been able to do my research in tackling complex problems for the last about 25 years or so. But is that the answer? Is it something else? Are any changes needed to facilitate implementation strategies? Can we do better to train, educate our students, as well as do our research? So those are just some of the open questions that I have. And I wanted to give you some things to think about tonight, things to think about in the future about how I think about science and what we're doing now. And I just want to end by saying, thank you to all of you for coming tonight, and thank you for listening.